Oscillator Noise, a basic training by me, Nick Amey from IQD Frequency Products. In this short presentation, we'll cover various types of noise that you can find from the oscillator output. We'll be covering phase noise, phase jitter, spurious noise, jitter, and Allan deviation. Oscillator, phase noise. So phase noise is a measurement of the power at an offset from the carrier frequency, and in the plot on the right there you can see the carrier frequency is measured in the top right as 99.99, so we can say 100 megahertz, and the carrier itself was actually 16 dBms. And then along the x-axis we're looking at a logarithmic scale of frequency shift away from that carrier. So the first line is 1 hertz away, and then the next chunk is 10 hertz, 100 hertz, 1000 hertz, and so on. And the yellow plot shows the power of the frequency components at that frequency offset. So the output is very similar to a spectrum analyzer, although you won't be able to measure phase noise using a normal spectrum analyzer simply because they don't have the resolution and they can't get that low. So you're going to need some specialist equipment to measure phase noise. This plot here was done on a Agilent 5052B, which I think cost us around the $100,000 mark. This equipment is getting quicker. When I started in the industry 20 years ago, it would have taken about an hour or so, maybe 2 or 3 hours on a really low phase noise plot to get an accurate measurement, and my engineers at the time told me that was very fast. These days, these measurements will take 5 minutes or so. On a really low phase noise plot, it will take longer to do the measurement. Might take an hour at most, I would have said. So yeah, it's getting quicker, it's getting better, but there's still needs a bit of time to do this stuff. When we are making a phase noise measurement, we need to be very careful about the test setup. Things like power supply, cabling, test fixtures, EMC shielding, these will all make an enormous difference to the measurements. When we do this, if it's a very low phase noise oscillator, we might use something like a lead acid DC battery for the power supply because they are very low noise. We might need to use fixed RF cabling. If I can tell you that if I twist the cabling, you will see the phase noise jump, especially at the close-in area. And any screening, I can measure the EMI radiation coming off strip lights, and CRT monitors were terrible for this in the old days. So yeah, very important to look at the measurement setup when you're doing this measurement. Yeah, generally speaking, the phase noise plot shows that there is more power concentrated towards the carrier and less as it falls away. We can say that this stuff close into the carrier is normally attributed to the resonator within the circuit, and the far out is generally attributed to noise coming from the amplifier and the silicon in the oscillator circuit, as a rule of thumb, that is. And so let's look at phase jitter. Phase jitter is calculated from integrating the area underneath the phase noise plot and within some bandwidth. So the plot on the right there is a phase noise plot, as we saw before, and below it you can see a specialized piece of software being used to calculate the jitter. And the integration bandwidth that's being used is 12 kilohertz to 20 megahertz, and the result is 8.3 femtoseconds. And you can see on the plot there's one yellow line which is at the 12 kilohertz mark, and the 20 megahertz mark is right out at the far end of the phase noise plot. So let's use exactly the same phase noise plot we had before and change the integration bandwidth. This time 637 kilohertz to 10 megahertz, and now we see 5.8 femtoseconds instead. And for a third time, let's use exactly the same phase noise plot again, and this time we'll integrate between 2 hertz and 10 megahertz, and we see 200 femtoseconds. So very different results depending on the integration bandwidth. So we've seen the same phase noise plot with 3 different integration bandwidths, and we see 3 very different results for the phase jitter. That tells us that the bandwidth is very important to check. Now, 12 kilohertz to 20 megahertz is the most common bandwidth that you'll see on an oscillator datasheet. And that's used by people in the oscillator industry because we need something to compare one product to another. We need some way to quickly explain why the phase noise and phase jitter on this product is better than that product, or perhaps we want to compare our competitors' products to our own and we want some commonality in the way that we do the measurement. But why 12 kilohertz to 20 megahertz, you might ask? Well, I had a little look on the internet and I found this information, and it tells me that 12 kilohertz to 20 megahertz in fact came from the original Sonnet optical fiber specs, and they were quite a long time ago when they were introduced. And you can see that the other integration bandwidths that I quoted there have come from other applications. So it's important to consider when you're looking at a phase jitter value whether the integration bandwidth is 12 kilohertz to 20 megahertz and therefore a good comparison between this product and another product, or is it in fact the integration bandwidth that's necessary for your application, or is it some totally arbitrary figure and shouldn't be used in comparisons at all. Now let's look at spurious response. On the phase noise plot on the right there, at the very far end we can see some spikes happening here. This is in fact coming from a complex system which has got a digital control loop, it's got some digital switching, it's got a processor running inside, and it's giving the user a lot of complex information about the state of the oscillator as it's running. All very useful stuff, but that digital switching noise does create a little bit of spikies on the phase noise plot. Where there are things we can do to try and move that away. So what we try and do as a design team is shift that to be outside the bandwidth for the phase jitter that we talked about before. And we can do that by slowing down the clock speed or putting in filters at specific areas. If we were going to specify that, we would probably have a spec that said something like spurious frequency of 80 dB C max, and that would be in reference to the main mode. So in this plot, the carrier frequency is 10 megahertz and 10 dBm, and we would specify that there would be at least 80 dBs between the carrier and the peak of whatever spurious noise was on the plot. Another way to quantify noise in an oscillator is to talk about jitter. Jitter is a time domain measurement rather than a frequency domain measurement, so it's normally measured on an oscilloscope. The plot on the right there shows a typical jitter plot, and here what you can see is a number of waveforms overlapped onto each other to form a solid block, because the time base has been pushed out to such an area that it looks solid on the scope plot. And in the top right you see an eye diagram, and in the top left you see some measurements. They're jitter measurements, and what you can see is things like a mean value, a max, a min, a peak to peak, and a standard deviation for various different types of jitter. And that's very typical of jitter. It's a statistical analysis of all of that data that's been measured there. To make a jitter measurement, you're going to need a scope with a very high sample rate, very high bandwidth, because you're trying to measure the exact changes in the rising edge and where that occurs over repeated steps. So yeah, we have to spend a lot of money to buy scopes with very, very high bandwidth. And what I have learned from this is that you can be careful when you adjust any setting on the oscilloscope. Very often the bandwidth jumps back to some default value, and you have to manually turn the sample rate back up to the maximum. So just a little tip there when you're playing with this equipment. We found that to be the case in most of our scopes. So when we look at jitter, it's a statistical measurement, as we said, of the overlapping pulses, and you're trying to establish how good they are to being perfect. Jitter can be broken into two areas. We can say that there are random jitter, which is unpredictable electrical noise and typically follows a normal distribution and can be caused by thermal noise in the circuit or things of that nature, as opposed to deterministic jitter. Deterministic jitter is more like the spurious response we saw in the frequency domain. It's predictable, it's reproducible, it can often be attributed to something very specific, and it has a non-normal distribution. And then from that there is total jitter, which is the sum value of the two. And as I said before, all these values are then discussed in their statistical terms. So what's the peak value, or what's the standard deviation, or some such like that. Jitter is used by our customers because often in a digital system one is trying to calculate a total bit error rate, and a good oscillator will reduce the jitter contribution within the whole system. So if we can get the oscillator jitter lower, then everything else's jitter will be lower, and so the total bit error rate will be improved. That's the objective here. And finally, for this presentation, let's look at Allan Deviation, or ADEV. ADEV was created by Dave Allan, and it's a derivative of the time interval error. That means that we take a series of pulses, we overleave them between each other, and we ask for every rising edge, how far away is it from what would have been a perfect waveform. So we do that over very long time periods. We build up an enormous data set, and then we do some maths to that data, and from that we derive what's the Allan deviation measurements. In fact, Allan deviation is the log-log plot of the square root of Allan variance, and I can tell you that mathematically this is very complicated to explain. In a short presentation like this I'm not going to try, but if you want to, there's a link at the end of the presentation to a video where Dave Allan himself, the man in the video, in the photograph there, does explain the maths behind it, and you can see on his whiteboard the complexities that's going on here. The point about Allan deviation is it's a very clever way of removing all the instabilities of an oscillator that are caused by systematic errors such as frequency drift, temperature and aging. So when you remove all of those things, what are you left with? You're left with a noise that cannot be attributed to some external influence. And as a colleague of mine explained, the point of Allan deviation is that you can then use that figure to compare the noise of one oscillator to the noise of another, even though the two oscillators are running at different frequencies and in different environments. So it gives you a number that you can use to say this oscillator is better than this oscillator, even though the two oscillators are not comparable when you look at the data sheets. To make the measurement, you're going to need a specialized instrument or a counter. The measurement has to be made on a gap-free instrument, so it can't, on a traditional counter, if you have a gate time of 0.1 of a second, it could be that the following 0.1 of a second, then there's a small gap between those two measurement periods, and that was a bit of a no-no in Allan deviation, and in fact there was a way mathematically to compensate for that, but that was very complex. Modern counters don't do that anymore. Most modern counters are what we call gap-free, so they're interleaving over each other. That's much easier for an Allan deviation calculation. So yeah, if you're using an older counter, just be aware of that. One other thing we would say from experience, that a lot of counters have got a noise floor of 20 picoseconds, which equates to 0.5 to the minus 11 at 1 second tau on an Allan deviation plot. So if you're looking at an Allan deviation plot and you happen to notice that at 1 second tau it has a figure of 0.5 to the minus 11, there's a fairly reasonable chance that that's caused by the instrument rather than the oscillator, and the oscillator is in fact better than that. So that's just something to be aware of. So the plot on the bottom right there is an Allan deviation measurement taken from one of our oscillators, and this plot, as we said, is a log-log plot. So along the bottom there we're looking at time, and we're looking at 0.1 of a second, 1 second, 10 seconds, 100 seconds, 1,000 seconds. and then the number that we're reading off on the y-axis, it doesn't really have a value that can be equated to some electrical or measurable thing beyond it being a quantity that you can compare to another Allan deviation plot from another oscillator and say this one is better than that one. So very useful matrix when comparing oscillators.